Hi there, welcome to the new video. So today we'll be going through the paper which is data augmentation using pre-trained transformer models. This paper came out in the year of 2020 in the month of March by Alexa AI. So at very high level, the paper essentially introduces the technique of data augmentation in natural language text using pre-trained transformer models such as BERT, BART, GPT2. The authors play around with classification tasks to judge how well each of these models perform when compared to the previous models that have been released for the same task. Okay, so let's move forward and see what are the nitty-gritties of the paper. Language model-based pre-trained models such as BERT have provided significant gains across different NLP tasks. In this paper, we study different types of pre-trained transformer-based models such as auto-regressive GPT2, auto-encoder-based, which is BERT, and sequence-to-sequence, which is BART. Let me give a quick refresher to all of these three models, and then we can move forward. So let's start with GPT-2. So GPT-2 is nothing but a language model. So by language model, what I mean, if you have a sentence, this is a dog. So if you give your model this much of the text, it is supposed to produce the word dog after this. So the model is essentially trained in a fashion of predicting the next word at any given instance. GPT is a decoder only model, which means at the input you'll be giving one word at a time, and output will be producing t plus 1th word at that moment. Then again that goes as an input in the next step and you produce t plus 2th word. So this is how the training is done. At every instance when you do a softmax over full vocabulary, you do a cross entropy to kind of measure the loss of how close you were to generating that word. So in the original architecture, they have some 12, 24, 48 number of layers that they define. So these are all transformer units where each of the units is based on self-attention and feed-forward neural network. So at any instance, let's say if you want to predict what is there at t plus 2th word, the model is only allowed to see what has happened in the past. So it can just put an attention to all the words that come before it, unlike BERT, which is bidirectional in nature and kind of peak on its right as well. Okay, now talking about BERT. So BERT stands for bidirectional encoder representation of transformer. So as GPT was decoder only model, BERT is the encoder only model. So decoder only models are usually good in doing tasks like natural language generation, whereas encoder only models are good at encoding a given information in some vector format that could be used later on by some decoding algorithms. So the pre-training of BERT was done on two subtasks. The first one was masked language modeling, and the second one was next sentence prediction. So for masked language modeling, the task was you given a sequence, let's say this is a dog, you mask one of the words out, let's say you mask out a, so the input sequence becomes this is mask dog. So all of these four tokens go through an encoder stack, and at output, you're supposed to produce each of the words, but at a time, the loss would be just propagating backwards based on what the model produces at that position of the mask token. The second task in which it was trained was you put in two sequences one after the other, and the model is supposed to do a binary classification saying whether S2, which is a sequence 2, comes after S1 or not. So that is the second task on which the model was trained. And let's see about the third model, which was BART. So this is a sequence to sequence model, unlike previous one, which were only decoder or encoder based models. So this has both the components of encoder block as well as decoder block. And the idea is to give a sequence of words S1, let's say, that goes through your encoder block, gets a thought representation, which is the dense representation of the full sentence or sequence, and goes to the decoder again and generates some output sequence S2. So the authors of BART essentially trained the model in a denoising fashion. So they introduced insertion of any random word in a sequence, deletion of any word from a sequence, then masking certain words from a sequence. So these three, or there could be more patterns that they infused in an input sequence, and at the output sequence, they would want a denoised version of the same sequence. So for example, this a dog. So here I deleted the word is. So this thing would go through encoder and decoder both the blocks, and at output, I would want to generate this is a dog. So this is the denoised version of what I would want to generate if the deletion was the operation that took at the input end. So this was the full idea around what these three models are that authors are mentioning in the paper. Now let's get back to the paper. They say prepending the class label to text sequences provide a simple yet effective way to condition the pre-trained model for data augmentation. So this is something really interesting. So what they are saying is, unlike previous work where people didn't use to consider class label at all while generating an augmented sentence, one of the ways people used to do it was get a word, find its synonym, replace that word with its synonym. One more way is how people used to do it was swapping two words that happen to be in a same sentence. So authors talk about this with an example. So they say in the case of sentiment classification, for example, if you have a sentence, a small impact with a big movie, which is a negative sentiment. Now, if you swap the word impact with the word movie, the sentence essentially becomes a small movie with a big impact. Now, this changes to a positive sentiment. So, these are the kind of problems authors are saying kind of confuse the model because now, while training, you will be giving the augmented sentence with a class label of negative, which is not correct in this case. So, what they say is instead, what we have found is if you prepend the class label, let's say you have a class label negative, then you have the full sentence, a small impact, blah blah, big. Now you would want to generate an augmented sentence A1 that takes in full of this context and it's also inherently conditioned on the class as well. So they found such a technique essentially creates more coherent and relevant text. So as they mentioned, they're trying three different pre-trained models, GPT2, BERT, and sequence to sequence, which is BART. They test their techniques on three NLP tasks, which is sentiment classification, intent classification, and question classification. And to simulate a low resource scenario, they go about just choosing 1% of the full training dataset and then doing an augmentation on top of that, and then finally training a downstream model on that set. Let's move forward. Okay, so they define this augmentation pipeline. So let's go through this once. So you have a training dataset that they define by dtrain. Then they define G, which can take any one of the pre-trained models. Then they fine tune G on the training dataset that they have and get a G tune. So now they have the tuned version of their respective models. And for each input sample, they would generate some number of augmented sentences. Okay, so they say we generate S is equal to 1 synthetic example for every example in the D train. So essentially, they are just generating one example per original sentence. Thus, the augmented data size is same as the size of the original data set. Okay. For conditional data augmentation, a model G incorporates label information during fine tuning for data generation. Okay, so what they're saying is after you have the pre-trained model, you fine tune it with the class information as well along with the original sentence. So that is the fine tuned version which they'll be using for generating the newer sentences. So they define two generic ways of conditioning the pre-trained models in the class label. First one is prepend, which talks about prepending the label yi each sequence xi in the training data without adding yi to the model vocabulary. So what this means is, let's say you have to generate an augmented example for sentiment classification. So for example, the sentence is, I hate this movie, and it was of negative sentiment originally. So they would prepend this class before all of the words in the sequence and then fine tune the models. So in case of BERT, it would be essentially masking one of the words and then predicting what comes at this position by considering all the words as well as the class label from the same context. For GPT, at any point you want to generate a word, it would be conditioned on all the previous words, which includes the class label as well. So for sequence to sequence, you'll be injecting some kind of a noise to this and pass it through encoder, get a thought vector, and essentially denoise it on the decoder side. So what they say is, when you prepend the label yi, we do it without adding yi to the model vocabulary. So since all of these models inherently use subword units as the tokenization scheme, so if your model doesn't know about the class label beforehand in its vocabulary, it's going to bifurcate into subword units and treat them as tokens. So this is the first experiment they do. Second experiment they talk about is the expansion. prepending label yi to each sequence xi in the training dataset and adding yi to the model vocabulary. So this is essentially the same thing what they're trying to do in the prepend. Rather, in this case, they add class label to the vocabulary and then fine tune the whole process. So in this case, the model will be considering class label also as a single token and won't be going further and bifurcating into further subunits. For all pre-trained models, during fine-tuning, we further train the learnable parameters G, its default task and loss function. So for all of the models that we saw, whether it was GPT, BERT, BART, the loss function that we try to minimize is cross entropy. So they're saying we use the same loss function and then train all the parameters that are there in the model. Let's move further. So for auto-regressive models, they're saying fine-tuning GPT-2, we create a training dataset by concatenating all the sequences. And this separation token between label and sentence, and EOS denotes the end of the sentence. Okay, so what they're saying is, let's say you have 10 reviews where each of the words in the review is said to be in the form of xi, and each of the reviews have a label yi. So what you do is you concatenate all the 10 reviews in such a fashion. So you have, let's say, positive sentiment, then you put a separator token, which kind of hints your model towards considering class label and input differently. Then you append all the tokens from the input sentence, and then you put end of sentence. So this is your first example, and you repeat this 9 more times for all the remaining sentences that you have. And then you essentially go about just training a language model, which is what GPT is. At any given point, it will just consider the previous sentences and produce the next output. So they've mentioned one interesting thing. We found that such generation struggles in preserving label information, and a simple way to improve the generated data label quality is to provide an additional context to G. Formally, we provide yi separation, some keywords as prompt where these are first keywords, and they use k is equal to 3. Essentially what they're saying is, after you're done with this kind of training, now when it comes to the inference part, so instead of just giving the class label, which is CI, if you give certain prefix words as well, then model generates really high quality data. Unlike if you just give class labels, model gets perplexed easily. So one of the intuitions why this is happening is, let's consider you have a space W, where W stands for world information. So the pre-trained GPT was trained on all of the Wikipedia books and common crawl text. So that is the whole world information that GPT has, and its vocabulary is essentially derived from that set. Now, when you fine tune your GPT, you are essentially creating a small cloud of words that is specific to the task in hand. In this case, it would be review words. So now when you just give class label, model knows it has to pick something from this circle. But the couple of initial words it would pick could be very common in the open world domain where it was trained. So chances are pretty high model would start from something inside this circle and might diverge to something that is totally outside that circle, creating something totally irrelevant and that is not in context to the given label. Instead, if you give class label as well as if you give couple of words, then chances of that happening are pretty less, because now model will generate the next word condition on the class label as well as these three words. So it is supposed to be picking words that are in this circle and create a trajectory of the sequence within this. Okay, so moving on. So for sequence to sequence generation using BART, BART can be trained with different denoising tasks such as insertion, deletion, and masking. But they found that masking performs better than others. Note that masking can be applied to either word or subword level. So they explored two ways of kind of doing a word level masking. One was replace a word WI with the mask token mask. The second was replace continuous chunk of K words with a single mask. Okay, so what they're saying is mask-based denoising performed well compared to insertion and deletion. So the way mask thing works is, let's say you have a sentence, this is a dog. If you want to mask it out, you would either do this mask a dog. So this is one way of masking where they have mentioned about masking the full word and replacing the keyword mask at this position. The second is they replace continuous words happening with a single token. So the other could be this mask dog. So this is the second format. So the way it would be trained is this thing goes to your encoder, you get a thought representation, then this goes to decoder, and decoder is supposed to produce full denoised version. So it will produce this is a dog. It should produce all the four words. So if you recall how T5 is trained, it is trained in the same format. Just in that case, you are supposed to predict only the mask tokens at this point, rather than outputting whole sentence. Okay, so they say we mask 20% of the words and fine-tune BART with the denoising objective, where the goal is to decode the original sentence given a mask sequence. Yeah, so this is essentially the same thing. Then they talk about model implementation, which is on the engineering side. I'll not go through that. Just to mention, they are using top P sampling, which is also known as nucleus sampling, while decoding. Okay. Then here they have talked about what were the labels that they had for all the four tasks they had. So these were the labels that were essentially appended with each of its respective sentence. Then the augmentation would happen. So for training, they had 6229 for this dataset. So they used just 1%, which is 61 samples. Whereas for testing, they're using the whole sample that was there. Okay, I guess we are done with the paper. Now, before I close this walkthrough, I just want to mention about EDA. EDA stands for Easy Data Augmentation. So I already have a video on this. I've done the walkthrough for the paper. If you're interested, I'll put the link in the I button. You can just check it out. Okay, so I guess we are done with the paper. Now I'd like to just tell some of my thoughts on this. So I found this paper to be really elaborate in terms of what authors have done. Just one concern what I have is they talk about using 1% of the data for the data augmentation, which is fine. But what about doing a fine tuning? For that, you'll be needing a hell lot of data for generating the tuned version of the pre-trained model. So what if that data set is not available? That I see as a limitation to this approach. Having said that, I feel there's still a lot to be explored in this domain of data augmentation for natural language text, and big companies like Alexa AI taking part in such research shows a promising future. So that's it. So if you like such content, do let me know in the comments, hit a like and subscribe to the channel, and don't forget to share it with your friends if they are interested. We'll meet you in the next video. Thank you.